clockwise. In this video, let me discuss about examples under complex form of Fourier series. Let me take the example. Find the complex form of Fourier series f of x equal to e power k plus x in an interval minus pi to pi. The given function is in exponential form. That is, the given function here f of x equal to e power k plus x, that is defined under the interval minus pi to pi. So, you know the general form of the Fourier series representation of f of x, isn't it? Let me show you the formula table for your reference. Under the interval minus pi to pi, this is general form, that is f of x equal to sigma n raised to minus infinity to infinity cn e power I n x, where cn is calculated by make use of the formula 1 upon 2 pi interval minus pi to pi f of x e power minus I n x dx. Suppose if the same function is defined as 0 to 2 pi means we make use of this formula, and for calculating cn we make use of this formula. If it is at 0 to pi means we make use of this formula, that is, this is general Fourier series representation. For calculating cn we make use of this formula. So now the function is defined under minus pi to pi, so this is the general form, and for calculating cn we make use of this formula. Let me first calculate the value of cn first. Okay, since the function is defined under minus pi to pi, so this is your f of x, and for calculating f of x, that is to give the general form f of x, you have to first calculate cn. So for calculating cn we make use of this formula, and after calculating the value of cn and substitute here, gives you the general form of complex Fourier series of the given function. Let me first calculate the value of cn. So that is equal to 1 upon 2 pi interval minus pi to pi f of x e power minus I n x dx, that is equal to 1 upon 2 pi interval from minus pi to pi, where f of x is given function e power k plus x e power minus I n x dx. So here what I am going to do is 1 upon 2 pi interval minus pi to pi, I am just write this as e power k product e power x. Is it right? So e power k plus x can be written as e power k product e power x, isn't it? So product minus e power minus I n x dx. Okay, so that is equal to here, the integrand is with respect to x, so e power k is a constant, so you take it outside of the integral. So e power k divided by 2 pi integral from minus pi to pi e power x e power minus I n x dx. So integrate this. So what we are going to do is, so in both of them in exponential power and also having the common term x, so take it outside, so that will be easy for us to integrate. Okay, so now cn is equal to e power k divided by 2 pi integral from minus pi to pi. So here we have to take x as a common term and take it outside. So if you take x as a common term, what you get in the first term, you have only 1 minus I n, isn't it? So 1 minus I n. So integrating this, you get e power k divided by 2 pi integral from minus pi to, now we are going to integrate, isn't it? So integrating exponential function, you get e power 1 minus I n of x over 1 minus I n. That is a coefficient of x in the denominator. So the limit is from minus pi to pi. So the limit is only for the x term alone. So you have to take this 1 minus I n outside of this. So you have e power k over 2 pi 1 minus I n. So within parenthesis you have only e power 1 minus I n of x with the limit from minus pi to pi. So the limit is only for x alone. So first you have to replace this x by plus pi and then minus lower limit minus pi. Okay, that is e power k upon 2 pi of 1 minus I n of e power 1 minus I n of pi upper limit over minus, coming to the lower limit, e power 1 minus I n, replace x by minus pi. That's all. Okay, so in your next term, that is cn is equal to e power k upon 2 pi of 1 minus in. So here write the first term as it is. In the second term you just take this minus to the front. That is what I am going to do in the next step. Okay. So then product you have e power 1 minus in of pi minus e power minus 1 minus in of pi. That's all. So what we are going to do is you just multiply this pi inside the parenthesis. Okay. So for simplification we are going to do like that in the next step. So 1 minus in in the denominator. So e power pi e power minus in pi, isn't it? Okay. I am just multiply and I have to separate. Minus e power, here you have minus, so e power minus pi, first term, isn't it? Keep this minus in your mind, and e power, this minus and minus become plus, so e power plus in pi, that's all. So you know already e power I theta is equal to cos theta plus I sin theta. Using this, and e power minus I theta is equal to cos theta minus I sin theta. So we make use of this here. So here e power k over 2 pi of 1 minus in. Expanding this, e power pi is a constant, so you just write it as it is. So this is of the form e power minus I theta. Instead of theta here we have n pi. So you have to expand this as cos theta, that is cos n pi. So here we have minus, so minus I sin n pi minus. Second term is e power minus pi of, this is e power I theta. Instead of theta here we have n pi. So cos n pi plus I sin n pi. That's all. So you know the value of cos n pi and sin n pi. The value of cos n pi is cos n pi, that is minus 1 whole power n. Whereas the value of sin n pi is 0. Since the value of sin n pi is 0, this term becomes 0 and this term becomes 0. So only here we have, instead of cos n pi you have minus 1 whole power n here, and instead of cos n pi here you have minus 1 whole power n. That's all. Simplifying this in your next step. So you have Cn is equal to e power k over 2 pi of 1 minus in of, so here e power pi, that is in product with minus 1 whole power n. That is your first term. So e power pi minus 1 whole power n. Then coming to the second term, minus e power minus pi is in product with minus 1 whole power n, isn't it? So minus e power minus pi of minus 1 whole power n. So minus 1 whole power n is a common term, take it outside. So e power k minus 1 whole power n over 2 pi of 1 minus in. So within the bracket you have only e power pi minus e power minus pi. You know already e power x minus e power minus x whole divided by 2 is nothing but hyperbolic. That is 2 times sine, hyperbolic sine of x. Okay. So I have to replace this by e power k minus 1 whole power n over 2 pi of 1 minus in of, I have to replace this as twice hyperbolic sine of pi. So instead of x here, this is hyperbolic sine. Okay, don't write this as sine hx. This is circular function. Sine of 1 finger gap hx, that is circular function. Sine h of x, this is hyperbolic. That is hyperbolic sine and then 1 finger gap x. Okay, both these two are different, not the same. Okay, this is hyperbolic function. That's why I write sine h. Okay, sine h 1 finger gap pi. Okay. Hyperbolic sine of pi. Here 2 and 2 being cancelled, your Cn. Okay. So we have, so what is your Cn we have calculated, that's all. So our Cn we have calculated here is e power k minus 1 whole power n sine h pi upon pi of 1 minus in. This is what the value of Cn we calculated. We start this procedure up to this whenever we have the numbers in the denominator are in terms of real numbers. Here look at the denominator. Here the denominator consists of the complex number 1 minus in. So to make it in terms of real numbers, what we do, as usual, you have to multiply both numerator and denominator by its conjugate. That is, conjugate of 1 minus in is 1 plus in. So you have to multiply both numerator and denominator of this term by 1 plus in, makes the denominator as a real number. Okay, so that is what we have to do. Okay, only in case of complex number in the denominator you have to do like this, otherwise you have to stop up to this. Okay, here in this problem we have a complex number in the denominator. Okay, so that's why to make it into a real number, we have to multiply both numerator and denominator by its conjugate. Okay, so now Cn, just now we calculated as e power k minus 1 whole power n hyperbolic sine of pi over pi of 1 minus in, right? Pi of 1 minus in. I just write this step. Okay, once again. So what I am going to do here is just multiply both numerator and denominator by the conjugate. What is the conjugate? 1 plus in divided by 1 plus in. So that is equal to e power k of 1 plus in of minus 1 whole power n sin h pi over pi of, this is of the form, you know the formula for a plus b product a minus b. This is of the form a, that is a square minus b square. So instead of that, here we have 1 plus in 1 minus in. If you are writing like that, you have 1 square minus I square n square, isn't it? You know the value of I square. The value of I square is minus 1. So minus 1 is nothing but 1 minus of minus plus. So 1 plus n square. So I have to write directly as 1 plus n square. Okay, that's all. Okay, so this is the value of Cn. Now let me substitute all these values of Cn in f of x, gives you the general complex form of Fourier series of the given function f of x. Okay. Hence, your f of x is equal to sigma n varies from minus infinity to infinity Cn e power inx. The value of Cn we have calculated as e power k 1 plus in minus 1 whole power n hyperbolic sine pi upon pi of 1 plus n square of e power inx. Here the summation is only for n terms, so take outside the remaining terms from the summation. Okay, so here e power k is a constant, sin h pi and pi. So take all of these outside of the summation. E power k hyperbolic sine pi upon pi. Sigma n varies from minus infinity to infinity 1 plus in minus 1 whole power n upon 1 plus n square of e power inx. That's all. So this is the general, that is a complex form of the Fourier series of the given function f of x is equal to e power k plus x, that is defined at an interval minus pi to pi. Up to this, hope you got a clear idea about how to find the complex form of Fourier series of the given function if it is in terms of exponential form. Thanks for watching. See you all again in my next video.